I am Ashish Verma. I am assistant professor in civil engineering department in Ishan Engineering College. Earlier we discussed about the section of the beam. So today we discuss about the placement of the beam. So according to the placement, there is two types of beam. There is singly reinforced beam or doubly reinforced beam. How we can modify it? This is a beam or singly or a doubly. So for the calculation of singly or doubly, we have to check. We have to check or we have to calculate for the solution of numerical. This is a numerical on based of singly beam or a doubly beam. So this is a numerical rectangular beam of section 230 into 600 mm of effective span of 6 meter and cover is 50 mm. Imposed load of 40 kN per meter. Use M20 concrete and Fe415. So this is a rectangular beam. First of all, we write the given data. Given data is width of the beam is 230 mm and depth of the beam is, this is the overall depth which is denoted by capital D. It is a 600 mm and effective span of 6 meter. Its length is also given, which is 6 meter, and cover is 50 mm, which is denoted by D dash. D dash is the cover and which is given as 50 mm. And this is the superimposed load is given 40 kN per meter. And grade of concrete is M20 and grade of steel is Fe415. Earlier video I introduced this, what is M20 and what is Fe415. Again I explain today. M20 grade, M4 is a mixture and 20 is a compressive strength of concrete. Compressive strength of concrete, and here is also another grade which is Fe415. So Fe415, Fe shows iron and 415 is a yield strength of the steel. This is the given data of this numerical. So width of the beam is 230 mm, depth is 600 mm, length is 6 meter, cover is 50 mm, imposed load is 40 kN per meter. M20 and Fe415 grade is given, where M is the mixture, where M denotes the mixture, and 20 is the compressive strength of concrete. F is iron and Fe415 is the yield strength of the steel. Because here is 50 mm cover, so this is a 600 mm is a capital D, which is 600 mm. So we have to calculate the small d, which is the depth. This is the overall depth 600 mm. Width of the beam is 230 mm, and this is the 50 mm cover of the beam. So for the calculation of depth, we have to minus this cover. So capital D is small d equal to capital D minus cover. So we got the value of depth. Capital D is 600 mm and cover is a 50 mm. So depth is 550 mm. Now this is imposed load, this is a live load. For this beam, we have to calculate the dead load. How we calculate this dead load? So dead load is calculated by this. So width of the beam and depth of the beam and density of concrete, which is density of RCC, not concrete. Density of RCC, which is 25,000 kg per meter cube. Here is the value is given in kilonewton. So we have to convert this value in kilonewton. So this is the value. When you convert this in kilonewton, this is the value you got. So RCC density is 2500 kilonewton per meter cube. So this is the formula. Capital B and D is the depth, overall depth, and density of the RCC is 25. So here you can write density of RCC. For this calculation, B with how much it is given? 230. But this is in meter cube. So we have to convert this value into meter. So this is the 230 mm. When you convert this value, you got the value 230. And depth is 600 mm. When you convert this in meter, you got the value 0.600 mm. And density of RCC is 25. It is a Newton per meter cube only. When you convert this in kilonewton, you got the value of 25. So when you multiply this all value, this is 0.230 and 0.600 into 25. You got the value 3.45 kilonewton per meter cube. This is the dead load of the beam. This is the dead load of the beam, and superimposed load is given in numerical, which is 40 kilonewton per meter. Imposed load is 40 kilonewton per meter. So total load is which is denoted by W, 40 plus 3.45. The total load is 43.45 kilonewton per meter. Now this is the overall load, which is 43.45. Now for the safety purpose, we have to multiply the factor load. So factor load is 1.5 into 43.45. This is why this is multiplied, because we take the safety purpose. That's the reason we take the value of 1.5. So 1.5 into 43.45, we got the value of 65.175 kilonewton per meter. This is a simply supported beam. For the simply supported beam, so bending moment formula is WL square upon 8. So W total all over load is 65.175 and length is 6 meter. So this is in meter, that's why we take the value of length in a meter. So 6 square upon 8. When you calculate this value, you got the value 293.287 kilonewton meter. This is the value of calculated bending moment, which is 293.28 kilonewton meter. Now we calculate the ultimate bending moment. Ultimate bending moment. For calculation of ultimate bending moment, formula is 0.138 FCK BD square. This is the grade for FE 415. In question, this is a clearly shows the FE 415. That's the reason we apply this formula. So 0.138. Our FCK is the M20, which is 20, and B, width of the beam is 230, and depth of the beam is 600. These all are in mm, not in mm. Apply this value into formula. Formula is 0.138 FCK BD square. 0.138 FCK is M20. So 20 B, width of the beam is 230, and this is the small d, which is 550 mm. This is the overall depth. This is the calculated depth, which is 550 mm. When you calculate this value, you got the value 550 you got the value of 192.02 into 10 to the power 6 Newton mm. When you convert this value in kilonewton meter, so what you have done, 192.02 kilonewton meter. So this is the ultimate bending moment. This is a calculated bending moment which is divided by B dot M, and this is a calculated. This is the ultimate bending moment which is divided by bending moment ultimate. So what? So we have to compare calculated bending moment or ultimate bending moment. So calculated bending moment is 293.28 and ultimate bending moment is 192.02. So here is calculated bending moment is greater than to ultimate bending moment. So when this situation is occur, this is a clear situation. We can see that here is calculated bending moment is 293.28 and ultimate bending moment is 192.02. This situation is occur. You always design doubly reinforced beam. Here we can say ultimate bending moment is less than compared to the calculated bending moment. That's the reason we always design doubly reinforced beam. So here is calculated bending moment. We got the value 293 kilonewton meter and ultimate bending moment is 192 kilonewton meter. So here is calculated bending moment is greater than ultimate bending moment. When this type of situation occur, you always design doubly reinforced beam. This is doubly reinforced beam. In doubly reinforced beam, this is a compression zone or tension zone. Reinforcement is provided in compression zone as well as tension zone in doubly reinforced beam. When a singly reinforced beam you design, you only provide reinforcement only in tension zone, not in compression zone. So this is a difference between the singly reinforced beam or doubly reinforcement beam. So this is the numerical based on doubly reinforced beam. How you can check the beam is singly reinforced beam or doubly reinforcement beam. I hope you understand very well. Thank you so much.